Welcome back, everybody. So this is the last couple of lectures about the series on amplitude analysis on the quest for Exotica. I know it's Friday early morning. You are wondering why did we start at 9 o'clock? I am wondering too. So so this series of lectures, I mean, these two are going to be a bit more dense, technical and specific than the previous two. So we are going to play and use things that we saw on Wednesday. And then from there, we're going to do that all the way to very sophisticated amplitude analysis for meso-meso scattering and other reactions. Okay. So I don't know if you remember, but at the very end of the second lecture on Wednesday, we ended up with a slide like this. And the idea was, regardless of if you are working on experiments or if you are doing lattice QCD simulations, in spectroscopy, we are always going to need to describe this set of data. For example, for the phase, there is no way around it, and it's the only possible path towards understanding the spectrum. So we have to do what we call amplitude analysis. Now, thing is, we don't know the explicit answer. We don't know the explicit formula because this could be solving QCD. There are many ways, many effective field theories and models depending on the regime, but we are not going to go that way. Today, we're going to use what we call a bottom-up approach, which is we are going to impose these first principles. Don't you worry, I'll explain the three of them. We already know unitarity, we don't know the other two. And we're going to just use these first principles and the data information, just using data from experiment or data from lattice QCD in order to obtain our circles. Okay? So first things first, because we're going to play with this, we have a particle A decaying to B and C, and let's say that A is at rest, then we can describe the system, the final state, with a given collection of quantum numbers. I don't care much about the details, and we are always going to use particles without spin, because remember our final states are going to be pions, kaons, etas, etc. But the idea is that we can describe this final state system. Let's say that we are describing everything on the direction of C, of the particle C, in polar coordinates. We will end up with something like this. So this is going to go many quantum numbers that we are not really caring about now. And then we will have part of the wave function that depends on the polar coordinates, right? Which means is this integrand, if you were to get the norm of it, would be called the intensity and would be basically the probability of getting events on this direction in polar coordinates, okay? What I care for you, well, first things first is to realize that this can be related to the amplitudes we're going to be talking about today. Remember, for angular momentum, because I'm lazy, I will be using either capital J or this QL. And the intensity, to calculate the norm, will be proportional to these functions. What are these functions? How are they called? Probably you know them. Spherical harmonics, very well. So you can calculate them. There are recursive relations, and if you go to Wikipedia, you will find tons and tons of tables. These are some of the simplest ones. Again, this is because the particles in the final state have no spin. Otherwise, this would be D functions, which are rather more complicated, but we aren't going that way today. So you know some explicit expressions, and we know something about the intensity. And you will see we will play with that later on. So also remember that we are taking a look at the states, particles, and so they have well-defined angular momentum. We just have to claim, well, you just have to state that our theory is invariant, is rotationally invariant. And so the angular momentum arises as a good quantum number. So our amplitudes, whatever we measure at the end of the day, can be described in terms of what we call partial waves. And this is doing a partial wave projection. And these are where, well, the functions where our resonances or states are going to live. So let's start by describing how to feed data. So we know that unitarity tells us the conservation of probability. This S matrix must be equal to the identity. So let's start by elastic unitarity. We have just one system. A goes to A. Pi pi goes to pi pi, and there is nothing else. In that case, it is no longer a matrix, right? It's just a function. It's just one entry of the matrix. So the function, the modulus of the function must be equal 1. Basically, in the angular momentum projection, we would say that S of L is equal 1, the modulus. This means that we can describe it as just phase. I'm using this, 2I times delta for convention. You could describe it as I times 5 and that will be your phase over there, right? What does it mean for t, for our actual amplitude? So remember the relation between the two of them. This means that for t, and I should have called this little one t hat, the relation is something like this. And I leave as an exercise to prove this relation. It's not very complicated. We can talk about that afterwards. So we know the way of describing these t functions. We have to invent something for this delta, and then we will be able to describe our data.
Can you remind us briefly the difference between t and t hat one more time?
Yeah, sorry. So I should have used t hat here. So it is just a convention of the way you define it. The difference between this t that I'm defining here and what I call t hat is just the phase space. So you can add it or subtract it. If you add it here, then the relation for the partial projections here, we have a phase space of 2 times q divided by the square root of s. If you define t hat, then the relation is 1 plus 2i times t, little t. So that is the only difference. It's just a convention. So you can use both. We use both. This one is basically, as you can see, it's kind of like normalized to 1. This one will always have the phase space inside. At the end of the day, it doesn't matter. I mean, you are going to measure some amount, and then the phase space is always there. You can add it, well, leave it there or subtract. So let's start by doing the simplest thing that we can for this delta function. So let's assume that we are at the threshold of the reaction. So you have 2 pions that are interacting right at the threshold, where the masses, where the energy is basically the sum of the masses squared. In that case, this delta, threshold is going to be 0, right? There's no scattering. They cannot interact because you don't have enough energy for them to interact physically. But if you are slightly above it, then you might have something that is not 0. Okay, we are gonna describe it in terms of Q. This is first order expansion approximation. Actually, it means that for T, this will be proportional to this parameter A. Can somebody tell me what is the name of this A? The scattering length, right? This is very important for us, and for many, calculation theory practitioners, knowing scattering, and also if you work to study nuclei, you might want to know about this in body reactions. If you go along this line and you use this approximation, then the total cross section, remember, and we will prove this today, and wait, the imaginary part of the little t is proportional to the cross section. So basically 4 times pi a squared. Okay, assuming that there is only one angular momentum that contributes to the cross section. So what happens when we feed data? Okay, let's say that you want to do something more sophisticated. So instead of using just one order for t, you're going to expand this polynomial, many parameters, 10 parameters. Fine. Do you think that you're going to be able to describe this? Well, how many do you need? Let's take a look at that. First things first. Why q to the 2n and not q to the n? Okay, you can think about that. The second thing is, if you remember, this phase is associated to a pole in the complex state. Can a polynomial in the numerator produce a pole? It cannot, right? So it doesn't matter how many parameters you're going to have here, you won't be able to describe the full energy value. You would need something like this. It's a very simple formula, but this is not describing everything as we saw on Wednesday. So we still need something more clever. We have some expansion for low energy, we have some expansion for the simpler states, we need something more general, right? Also, is this parameterization unitary? What do you think? This is a unitarity relation. This is preservation of probability. Is this parameterization unitary? I mean, let's do it. At first order, this is A times Q, right? But this is the imaginary part of A times Q if A is real. It's 0. But what is this part? It's A squared Q squared. So no, it's not unitary. We are breaking preservation of probability. That's not good. So let's do something that doesn't break the preservation of probability. Something that allows us to respect unitarity. Then we will expand and put some explicit formulas over there. You can write, and well, you can play with this, or you can do it as an exercise. It's related to the previous one that I asked you to do. You can write t in this way. But this is going to be a function, the tangent of delta. and then this is the phase space rho. It's back here, but this is kind of breaking. This is the square root of S divided times Q. This is the phase space of the reaction. Now, this formula is unitary by construction. As it means that I can get an explicit value for rho or Q times cotangent. And whatever I put in there that makes sense with respect to unitarity. Okay? If I put 1 over Q, 1 over A, I recover the expansion that we had before. As an approximation. For example, let's relate this to lattice QCD. What would happen if we have some expansion like this inside a box? How do we know what we are looking for? So if you had a box like this, and then say that you have 2 pions inside the box. These 2 pions, as we were in a box, are quantized. So we will produce some energy levels depending on the mass of the state, the excitation, and the momentums of these 2 pions, right? So basically, the ground state, they don't move. Quantization of one of the pions moving with 1 unit of momentum, 2 units of momentum, etc., right? Now, what would happen if you had repulsion in the system? In this customary, but not so customary definition of the scattering length, if they are negative, then we will have repulsion, which means that the energies that we see on the lattice, on the box, at the end of the day, are higher than the non-interactive ones, right? Why? Because they are repulsing each other, so the energy increased. If we had attraction, then the energies would be lower, right? So this is more or less when you see you're playing with lattice QCD and you have your levels on a box. The first thing you should do is compare to non-interactive levels and see if you have an attractive or repulsive system. And, depending on the strength of the system, these lines will be displaced more or less from the non-interactive levels. Yep.
I'm sorry, can you also remind me what Q of S is?
Q of S is the momentum of the particles in the center of that momentum thread.
Is that the norm of the momentum?
No, this Q is the momentum.
Okay.
So basically, for example, for a system with equal masses, let's say that you have 2 particles with equal masses, Q would be something like the square root of S minus 4 times M squared. And then,
but it's a scalar quantity, not a vector.
Oh?
It's a scalar, not a 4
oh,
vector.
this is a function. It's not a vector, it's a function. So, oh, yeah. Okay, I got it. Yes, sorry. Is the modulus of the yeah. So, yes. So, once you have this formula and you know it's unitary, and you can expand it in whatever series you want, you get something like this. This is not the same as expanding T, right? Expanding T would break unitarity, but expanding ecotangent will not. It will always respect unitarity, the way we define it. So you can describe the low energy region, but you could also, in principle, describe this energy region, the resonant one. So how does this pole arise in our system? It is simple, right? This is the formula. We have a denominator. So if you want to have a pole, well, this part must equal this whole part, right? It means whenever this expansion has, 1 unit of imaginary part, then this will have a pole. This won't happen in the real axis. If these are real in the physical region, this cannot happen. But this can happen very close in the complex plane, which is where the resonance exists, right? This is what we were doing the other day. The resonance doesn't live on the real axis, lives slightly on the complex plane. So we found ourselves a very simple way of describing lattice QCD data or messy data from X-ray. And yes, we can describe something like this with a parameterization this simple, quote unquote. It's very simple yet powerful. Problem is, we were talking about elastic scattering, so everything were functions. How do we describe systems with lots of finite states? So let's see, we have A and B, pi, and then we are at an energy where we can have many different products, not only pi, but also k bar, eta, 4 pions, right? This is just a function. So you can only describe the elastic case. So let's move into that. This is called, what we are going to do is called the K-matrix approach. It's very simple, customary, we all use it nowadays, and it's powerful, as you'll see. So the first thing is, we're going to assume a first order approximation. Let's say that we are close to a resonance, okay? This resonance can decay to many possible channels. This is going to dominate the partial wave close to the resonance. And this is going to be a matrix, because now we have inelastic scattering. So the amplitude T of little t of L, is going to be equal to K, where K is the propagator of the resonance at first order approximation. We are assuming that this resonance has a very small width, and so we can describe almost as a propagator, and this indicates too many possible channels in the past. Now, because K dominates T, we can have more orders where K really scatters with itself. So the first order would be just K. But the second time, K would decay to all the possible intermediate channels, and then these possible intermediate channels would produce a K again, so the propagator again, that could decay, and then would scatter again, produce the propagator, scatter again, produce the propagator, so on and so forth. So you can keep expanding the series. And what kind of series is this? It's a geometric, right? If you get this formula, and then back all the terms, then you recover this function. You don't really need to do that. You can always define T in this way. There's no problem about that. It's just mathematical construction. This is just a hand-wavy way of motivating it. But the idea is this: if you have resonances that decay to many channels, and if you have many resonances, I was asked on Wednesday, what happens when many resonances decay to the very same channel? Well, this is going to work very well. So we will see. But again, it's a mathematical construction. You can define it from the very beginning without doing any of this. I could have just introduced it and introduce you to the mathematical properties of K. Okay? You can also rewrite it this way. And this is basically, remember, this is the inverse. So the numerator is equal to 1. So the numerator of T can be made equal to 1, and everything can be put in the denominator as the inverse of this object. And we will play with that in a second. So now, what are the properties of K? There is a mathematical construction. I can define the partial in terms of this K matrix, and then I can define some basic properties. Well, the first one is time reversal. So our theory, we are going to assume that A going to B and B going to A are the same, and so it means that, so the order doesn't matter, and it means that K is going to be equal to the transpose. Okay? So K is equal to K capital T. One. The second one is unitarity. Remember that it means this in matrix form now, because we are no longer in the elastic region. And this, if we look at the formula for T, you can rewrite it as in this way. And it also is an exercise. There's no complete. Yeah.
Is there, when you're gathering things into the geometric series, is there an obvious reason why rho of S times K is like bound between 0 and 1?
Rho of S times K.
I never understand the argument when you do the like resummation and then they say, geometric series, but I know that the argument has to be between 0 and 1.
Oh, okay, understood. So you're asking me, why do we know it converges?
Yes.
Well, as I say, it's a wavy way of proving this. You don't really need to do any geometric series that works. Because you can just define it that way. And this respects unitarity as an algebraic construction. So you know what I mean. You don't really need to think about a series that converge. But you know, K as a propagator will always have a given coupling that is 1. Because it's a propagator, this thing is a bare propagator. This thing has a coupling that is ordered 1. Okay. Well, not ordered 1, but you know, some G square function. And the idea is that you are going to assume that you are in a region where those couplings times the phase space are very small. And so in that way, this wavy expression can converge.
Okay, thank you.
So basically, if I'm not mistaken yet, so the idea is if you put here a bare propagator, and we will see the explicit formula in a few slides, then in the numerator of this propagator, you will have G squared divided by S minus M squared. Okay, that is the formula for the propagator. This G squared can now be related to the width of this object. Okay? We will see in a second. So this G squared can be related to what we call gamma on Wednesday. If you all remember, gamma was this, what I call now, the width is the inverse of the lifetime. Okay? So now this gamma must be very small for this approximation to work. Because if this gamma was big, then this thing could be described as a propagator. So if I am doing it's kind of a circular argument, right? If I am doing this approximation, it's because I am assuming that the G squared that is related to gamma cannot be very big. And so the whole thing has to converge. Otherwise, then I cannot start with this action. But as I said, this is just a handwave rule. You could have started with a mathematical definition like this, and then just keep going. Okay. So now we have time reversal, which means this relation, and the second one is unitary, which means that S times S dagger is equal to the identity. Also, it means if you play with that, if you calculate S times S dagger here, you are going to end up with the rest of KL minus K dagger L. And this is only unitary if KL and K dagger L are equal. Otherwise, you broke unitary. What does it mean for K? So we have that the entry AB is equal to BA, and that the entry AB is equal to BA complex conjugate. So the entry AB is equal to what? To the entry AB complex conjugate, right? We combine the two. This just means that K is real. And that is a basic property of the K matrix. At the end of the day, we can describe T with a K matrix, and if the K matrix is real, everything makes sense. Okay? And now we can accommodate or parameterize this K matrix. For example, in the elastic region, this formula that I presented to you before is just the K matrix approximation, well, the K matrix approach, sorry. Yes, the inverse of the K matrix is equal to this. Okay? The way we define everything is the way. So let's take a look at this toolkit now. So we can describe either in the elastic or inelastic region everything in terms of this K matrix approach. So this is K inverse. So there should be an inverse there. I don't know if I'm typing it or I didn't put this right. But the idea is, if I expand this in terms of a polynomial or the inverse in terms of a polynomial, we can recover some elastic things. This is now a function, the matrix, so it's no longer coupled setup. So I can describe elastic region, low energy or high energy, doesn't matter, describes unitary, it's fine. If the data is very complicated and we have many final states, for example, here I presented you a pi measurement from an experiment, we're going to play with that. But this is not the only state that is open. In this energy, from 1 GB to 2.4 GB, there are many other possible decay points. For example, where does the threshold of 2 kaons open? Remember the mass of the kaon? Is 0.492. 0.4926, yeah, depending on the kaon, more or less. So almost 0.5. So at 1 GB, 2 kaons open, right? So 2 pions here can decay also to 2 kaons. So this is just one of the many final states that we can measure and experiment. And we want to describe all of them. Okay? So here we are going to use a K matrix. We are going to use an actual matrix, not a function, to describe this data and the other channels. Now, this also answers the question that I had basically discussed about on Wednesday of what happens when many resonances decay to the same final state. They become something that overlaps. Are they simple enough? You see 3 peaks, and these 3 peaks are not going, they are not very far away. So they are overlapping. Actually, you see 4 peaks. There is a resonance in that tiny little one. And then, well, we are indeed describing the data. Indeed, this fits in itself. So you can get all these resonances properly with this kind of approach. So you define a matrix where the number of elements and the number of rows and columns will be the number of final states that you are going to have. And inside that, you parameterize. And as I promised, this is the formula that you use typically for the propagator part, so for the resonance part. 2 couplings, the mass, the bare mass of the system squared times S, and there's a term that is usually smooth. And this can be parameterized many ways, like a polynomial with different variables, something very simple, very complicated. But the resonance part, usually the poles come from this one. Okay, so let's take a look at my fields. So let's go to the elastic field. So this is another reaction, I scattering, and there you have lots of data and a field that goes to the data. Actually, you have to. They split here depending on the solution, but let's forget about everything that is above this dashed line. We're going to focus on the elastic field. So we are going to revert back to a function, no longer a matrix, just a simple function, okay? And it's going to be this parameterization. So if I go and feed the data, I'm going to feed it myself. So I parameterize this to tangent, and then I end up with fields. Now, this is just the real axis. This is where experiments live, right? You don't measure things in the complex plane. You measure things on imaginary energy. And this is this red line. This is actually the modulus of this function that I fitted there. This actually corresponds to that. So this is the phase shift, this is the modulus. Yep.
How are you looking at that plot knowing that the red box is the elastic region? How do you know that that's the elastic region?
Oh, yeah.
Looking at the plot?
Yes. So this is pi again, as I said, right? So it starts at 0.28 GeV, 140 MeV more or less. And so what else can appear here in the strong form? There is a channel that can open in that region, that box, apart from pi. It's 4 pions, which opens at like 640 MeV. But 4 pions are so tiny, this energy region, that perhaps you allow me to neglect them completely. Okay. For sure that is zero. And we have never determined that experimentally to be different from zero. So first order, there's only one channel open, pi. So it can only indicate pi. If you were above this box, what is this? This is 1 GeV. So once again, one channel opens over there. 2 kHz. So then of this box, you do have open channels. Because 2 kHz and 2 pions couple very strongly. That's also why you see this super rapid phase motion right over there.
What is the initial state of the decay again?
This one is pi. So pi drive with each other. They can produce something, and then they decay to pi. So we will see that there is something here. Even though this say, right, this line say, doesn't look at all like the right inner one that we described before, but there is still a state of it.
And what's the 0.6 to 1 GeV?
The 0.6 to 1 GeV.
Yeah, the data from 0.6 to 1 GeV.
This one.
Yeah.
So that is usually, well, that is a part of the connection of the CERN-Munich collaboration. So CERN-Munich experiments that were done in the 70s, 80s at CERN.
I mean, what channel?
Oh, this is pi. This is pi to pi.
So I thought up to 0.4 was pi.
No, so this is what you measure in the final state. In this, the whole plot, the final state of the whole plot is pi. So you go on experiment, you have your interaction, and at the end of the day, you get some hits, right? And you can select the final state that you're measuring. This one is always pi. Now, the way of describing it depends on if there are other channels coupling to pi. Because if there are, I should put more than just one plot here. The plot to pi, and then the plot to KK, and then the plot to many other channels that couple to them, right? And it has to describe all of them together. And this is the K-matrix approach. You will have to describe all of them together to fulfill unitarity. Okay? But because I am neglecting all the rest, well, not that I am neglecting, all the rest are closed, what I can hear is only about pi and final state. So pi can only go to pi. So in this region, we don't have to look at anything else. Now, if we were looking above this region, we would have to take a look at all the possible channels that are measuring this or other experiments. And then you can see the plots, right? But you don't have to do that. So in this, I mean, it's a very simple line. It's kind of like a straight line. It goes through the data, it has a good chi-square. And if I go and instead of plotting just the real axis and the value for the phase shift, I plot the modulus of the amplitude in the complex plane. So now, this is invariant mass. So this is this part here. And this is the imaginary part of this variable. So this is that I extend this variable and I elliptically continue this variable into the complex plane. And I plot the modulus of it. And this is what you see. This is actually that thing. Okay? So first things first, what is this? Why is this continuous? Aren't you wondering about that? Perhaps you know the answer. The second one is, well, you told us that there are poles close to the real axis, but there are no poles in here. Okay. This, by the way, is the fact that in here, this is a smooth, is called analyticity. And it's the second of the three first principles that I talked about. Let's, in a non-relativistic way, prove this. So let's say that we have an incoming wave packet. So we're going to have our pions, we produce a wave packet that can be different in shape or size, but we are never going to care about the actual function that creates this wave packet, only its basic properties. And we are going to scatter the pions. So we have the incoming wave packet, we send it, then they scatter, and we get an outgoing one. We can mathematically relate the two through the S matrix. Remember, we usually subtract this -1 means the trivial non-interacting part of the S matrix. So we take it out, we get this part, and this produces a relation between the outgoing wave packet and the incoming one through a function. I don't know the explicit value of this function. I don't know its algebraic value. This is QCD. I don't know. But let's take a look at something very simple. Do you think that in an experiment, when you detect pions at the end of the day, they are going to show up before you send the beam? So you didn't switch on the machine, but then you start getting pions in your chamber. And that would be awesome. And then neutrinos, end up flying faster than light. But it doesn't happen. In any theory that we know that makes sense, the theory must be causal, right? Things happen, the consequence happens after the cause. And so it means for us that t, which is the final value, must be always greater than t prime if we want to get something. Or this function must be always 0 if t prime is greater than t, because it cannot produce any effect if it doesn't happen yet, right? So this capital G function, which value I don't know, related to G's little g, looks like this, just because of causality. Okay, still, we don't know the explicit value for this, but we know it must be causal, it must be well behaved. So because this capital G function that is going to relate the scattering, the outgoing wave packet with the incoming one, looks like this from 0 to infinity because of causality. Now in the upper part of the energy plane, let's say that we're describing everything in terms of the energy, in the upper part of the complex energy plane, what do we get? We get a real value for the energy, right? Plus I something. Now, this exponential, I times I, is a minus, right? So in the upper part of the complex energy plane, we could get a decaying exponential here on the integral, which makes everything converge. So this function is well behaved, and so scattering in the upper part of the E-plane is well behaved. There are no faults. Now, if you live in the lower part, this will be a different story, because we will recover an exponential that grows. And so this integral will be well defined. But let's say that we're only in the upper part of the energy plane. Now, I squared it. Where does the upper part of the energy plane go to? When you have the face of a complex value and you square the whole thing, this becomes twice the face, right? So the upper part of an energy plane from 0 to 180 becomes from 0 to 360. So in the E square variable, which is what we call S, right? Is the Mandelstam invariant, is E squared. The function is well defined, well behaved in the whole complex. And this is what we just do. There are no poles there. Okay? Where are the poles? I promise you there are. Where are they? Well, first things first, what is this jump? I keep plotting modulus of amplitudes, and they all have this jump between plus I epsilon and minus I epsilon. Well, this comes out of what we call the spar reflection principle. It's a mathematical theorem. I'm not going to prove it. It's not very complicated. But the idea is that if you have a complex function that is well behaved, and it has some real values in the real axis somewhere, then this relation always holds. We just prove that our functions are well behaved. So they do respect this principle. Either S or little t. We don't care. So now, why do we have this jump? Well, this jump is just the difference between t of S plus I epsilon, right? Minus t of S minus I epsilon. That is the definition. And this, by the spar reflection principle, is as t of S plus I epsilon minus t conjugate of S plus I epsilon. What is this? This is just 2i, the imaginary part of t, right? The function minus its complex conjugate is just 2 times I, the imaginary part. So wherever we have an imaginary part for the function, we have a jump. The greater this imaginary part, the greater the jump. Okay? Very simple. You play with this actually for years. The square root function in the complex plane has this. I don't know if you were introduced to them, but you should have. They are called multivariate functions in complex analysis. You were introduced to the square root, you were introduced to the logarithm. All of them have these branch cuts. Whenever a well-defined function in the complex plane has an imaginary part, and this is why I'm plotting here square root of minus s, or minus x if you want, then it will have a jump. Because if you look at the faces above, then this will have no face. You will look at the face at 360 degrees, is this, right? So one is I, the other is minus I. What is the jump? It's 2 times the imaginary part. So at x equals 1, this is just 2 times I, right? It works. And this creates a complicated structure of what we call Riemann surfaces. So basically, the idea here is we have the square root function. Now we just discovered that it has a jump. And then you ask me, hey, what happens if I go in this direction? I want to continuously go in this direction, or I want to go continuously in this other direction. Well, you end up getting something like this. And this is the square root. This is beautiful. If you go in this direction, it's going up here. Keep going, well, and you connect continuously to this other that comes into and enters into this one. You see? So the 2 Riemann surfaces in here are connected. So this function has a 2-sheeted Riemann structure, 2 sheets. The first sheet is the one where you define everything, and the second one is hidden, that you can also calculate. And this is where the poles live. Okay? By the way, this is also the proof of the optical theorem. As unitarity tells us this, right? We define this for the t function. But now we just calculated that t minus t dagger is equal to the imaginary part, 2 times I the imaginary. So basically, this is equal to the sum over all possible scattering effects, which is the cross section. So whenever in an experiment we measure data, there is some scattering, then the imaginary part is different from 0. And so we have this. So first, see the structure is clear through poles. You define, you feed the data. This everything is very clear. And now you go directly through this. Boom. You have a pole. This is the signal results. So there is a state here. There's a pole. And you see the line shape of this doesn't look anything like we were seeing before. If you are playing with bright linears, this doesn't look at all like the simple parameterizations. But there is a state over there. So because I'm running out of time, we're gonna skip some other details. But so let's say we can get, and we can play with this after the classes, or as an exercise. We can get an explicit way of going from the first sheet to the second one. So it makes everything very simple, because if we know the parameterization to the fitting in the data, then we know how to handle poles algebraically. Okay. So any questions here? If you don't have something very relevant, it's better maybe to do it at the end, because I'm running out of time. But if you have something urgent, yeah, just carry you in this. So now this is more dense. I'm sure of that. So let's play with what we just learned. Okay, so this is going to be simple. We're going back to play the school plots, no maths. So, mostly no maths. Remember the quark model? Maybe you remember that we calculated the possible quantum numbers for a quark and an anti-quark for meshes, right? Are given in this table. You saw them on Wednesday. So do you see a 1 minus plus in this table? No, you do not. So I was asked on Wednesday to explain why was I calling this 1 minus plus hybrid. And so the idea could be something like, we are just going to revert one of these parties of the 1 plus plus by including a gluon. This is going to revert the part. However, when you see a theoretical predictions coming from models or from lattice QCD, you see a prediction of one single hybrid state. If you go to the PDG, to the book, then you see 2. This is very problematic, because it means that we are not understanding anything, right? So we're saying that we do this to understand QCD, to gather information, Turns out we just go over the corner and we got everything wrong. So let's take a look at those states. So we are going to use a fantastic experiment called mass at CERN. So they use very highly energetic beams, ion beams, and let's see what they measure. First things first. This hybrid, as I said, is 1 minus plus in JPC. Let's start to take a look at the possible lightest states. So can it decay to pi k? It doesn't have a strangeness, so it cannot decay to pi k. Can it decay to pi pi? But these are the changes in quantum numbers of pions. And then if you combine them because they are identical particles, you have to symmetrize and symmetrize according to the rules. It means that we do not have that final state in pions. So no, the hybrid cannot decay to 2 pions. But it can decay to a pion and an eta, or a pion and an eta prime. We also played with this because they are no longer identical particles. So this is a way of describing the system. And yeah, we get a moment plus yeah.
In final states with multiple particles, do we need to be concerned about the relative orbital angular momenta between them?
For which specific?
In terms of the possible final J states that they can produce.
Well, so the idea here, of course, is that the total angular momentum of this object, right, is 1. It has spin 1. So if you have 2 pions, they don't have a spin. So you will have to have a state where the 2 pions combine with a unit of angular momentum to create this J equal 1, right? And that means something on the permutation relation because they are identical particles, right? This is exciting how you don't get that number. Because the point here is that pions and etas have the same quantum numbers. The final state is different just because one you have to combine in a specific way depending on the angular momentum that they have it. The other one, and the other one does not. Yeah.
In that case, is it accurate to say that if we had even like a 3-body decay, we wouldn't be able to make a statement about the distribution of those angular momenta?
Yeah, it's very complicated for a 3-body decay, right? Because whatever you recombine on 2-body final state will be also recombined with a 3rd one. So there are many possible ways of getting the same J, where 2 of the systems can have like a tower of partial waves. So I'd say, as a rule of thumb, it's going to be very complicated to just state what is the exact set of angular momentums on each one of the 2 invariant systems. Right? You can do 3 permutations, so it's going to be complicated. I mean, still, sometimes you can do. So there are some cases we can talk about that later. Where you more or less can guess it. So let's take a look at this. So we have the experiment. It's a very nice experiment, relatively new. It collected lots of data and it has very nice kinematics for us. 1 minus plus, so eta pi or eta prime pi final state, and these are the invariant masses. So this was measured. These are data from the experiment published. What do you see? Well, we see 2 peaks, and they are not at the same mass. So one of these peaks is roughly 1.3, 1.4. The other is roughly 1.8. And this is what motivates, well, because it was also seen in other experiments, the plea to claim that there are 2 states. But as I said, this basically is telling us that we didn't understand anything here, because all theoretical predictions and lattice QCD predictions said that there was only 1 state. So who is wrong? Is the experiment wrong? Is the theoretical expectation wrong? Is something else that we are doing that is sloppy? It's got to be this one. So remember the definition of intensities? I told you that they are proportional to these spherical harmonics. And then we can see it here in the data. So this is the amplitude, not the partial prediction. Eta pi final state, eta prime pi final state, and this is the cosine of this theta. What do you see here? Is it this kind of, you remember when you are looking at chemical orbital potentials, these different shapes and sizes and the geometries, right? If you take a look at this, you have accumulation of events in here and over there, symmetric. It's 0 and it's also 0 in the corners. So this is equal to J equal to. So this is dominated by a tensor group. If you just calculate these spherical harmonics, you will see that this particular one has this expression, which describes very well the amount of events that you see. These are just hits in the detector. But this is what we are counting, right? We're looking for this eta pi in the final state and we are counting each one of them or plotting wherever they hit. So this system is dominated by a j equal to by a tensor resonance. This is not the one we care about, right? We care about something that has j equal 1. Well, the second one, eta prime pi, looks like a combination of this function and this other function. So there is both a tensor, a tensor and a vector in eta prime pi. This is the angular momentum we care about, j equal 1. Okay, so maybe this is pointing to the fact that eta prime pi is going to be dominant, even though you remember the phase space to eta pi is greater because it's lighter. So your rules of thumb implicitly of all these points. Now, I was about to say bonus points for whoever tells me this m equal plus minus 1. Why does it dominate so hard instead of other projections? And I thought that you don't know all of this, but you do know all of this because they told me Matt introduced the Pomeron. So this is a Pomeron exchange, and this is what is driving these projections to be plus minus 1. The idea is this is the total reaction that they are measuring. Okay. Now this vertex is very simple. We're going to forget about that. This is a constant. Okay. This is the reaction we tell. How do we describe it? If we invoke unitarity, then we know the unitarity for the scattering part. So eta pi going to eta pi is equal to rho, whenever I put here a loop with some dashed vertical line, this means rho, and t times t complex conjugate, or the modulus of t squared. That is the unitarity that we know about, and I'm just doing a diagram to represent. What is the unitarity for this diagram? Well, kind of the same. We have the diagram again, in initial state, then the loop with the vertical dash line, and then re-scattering at the end. So this is the form. Rho, A, and T complex conjugate. Knowing this, we can know the formula for the amplitude. So this is the amplitude that is going to describe what they measure in the experiment. Now, remember that D can be described with numerator equal 1. We can always do that, as I said before. We can always put everything in the denominator. But now, because we have a term that is like a production term, we're going to have something different. Typically, you would assume at first order that this is a constant. And because it's not exactly a constant, we're going to put a smooth numerator. So something that varies very little. Actually, we're going to put some parameters and we are going to allow the data to tell us if we are right or not. But we will be right. Now there is a denominator in the formula, which has to be this one. And it's indeed what we are using. So this is the denominator for the scattering part, and this is the denominator for this function. Now, this is identical. As I said, sometimes I use J, sometimes I use QT, QL, because I'm lazy. And this part, let's forget about that first. We are going to do it in the next lecture. This is just a fancy way of grading this. Okay? So dispersion relation. We're going to talk about those in the next lecture. The idea is, by doing the same for the denominator that we do for scattering, by just plugging in and numerator, we're able to describe the data very, very well for several passaways and several final states. So we are describing the two peaks now, and this was a field of ours. And you see that the formula that we're using describes the two peaks. Another question is, did you find two particles? The answer is no. We found just one. When you go to the complex plane, to the second Riemann field where the poles live, turns out this guy is this guy. So there is one pole that is decaying slightly differently to the two channels and producing two peaks. And this not only reconciles all the theoretical predictions, lattice QCD predictions with data, but it's also kind of a way of saying, look, we must start doing something more elaborated for spectroscopy, or otherwise we will be fighting over these peaks producing weird things for years. This controversy actually lasts for around 20 years. So it wasn't something for like a few months. Now, it was soon after confirmed by some experimentalists. You might know the name of one of the organizers here. And then it was also soon after confirmed by our lattice collaboration in here, Jefferson Lab. Well, the lattice spectroscopy collaboration has been. We can also do this for other reactions, and I ran out of time, so finishing right now. We can do it for other very complicated reactions. For example, one of them is the mighty glue. If we look at the glue ball channel, and we are looking for reactions that can produce glue balls, this is a fantastic. Now, somebody will tell me, hey, look, you told us on Wednesday that glue balls are suppressed over other things. Why are we looking at this now? Well, if you find a way of connecting a CC bar object like the jet side to pions and kaons through continuous quark lines and QCD, well, then give us a call. Otherwise, it must be connected through something else. So in this case, we are looking at CC bar object going to live quarks, so it must be connected through gluons. And this is the cool thing, because it must be connected through gluons in this vertex. Whatever particle arises there must be a glue ball, right? If there was only one particle that appears here, it just connects to glue balls. It must be the glue ball. So this is what we call the golden channel for the glue ball search. And indeed, we can feed that data very well with these customary parameterizations that I introduced today. You see here all these resonances that we were talking about. This was actually the channel that we were looking at. And the interesting one is this one in the middle. That is the KK bar channel. That's a huge. So basically, by doing analysis like this, you can find these faults in the complex. Many different particles. So I promise you, there are 4 particles interacting here. So it's highly non-trivial, but still, we can find it with precision and robustness. But we can also tell you that this object that we talked about on Wednesday for a brief moment, it is called the 1710. It's a predominant glue ball. It couples to gluons much more than the others. Now, this has been debated also for many years, and it's always been expected to be the glue ball because if you use a quark model, it predicts the non-net, right? But there is a 10th state here, which is this one. That cannot be predicted by the quark model. And so many people have been working on this for many years, but this is one of the most robust extractions of its coupling parameters to the gluons. So yeah, we can do analysis like that in amplitude analysis and answer some questions that have been debated for many years. So I'm going to stop here. We'll continue the next one. Questions?
Questions, guys?
I see a difference between Wednesday, where we were all like very energetic and it was so very nice. And today, perhaps it was too dense. No questions. Thank you, Jose.
So in Wi-Fi scattering, sometimes people make use of this omnes function to
Yes.
guiding, but so that is only valid, so it cannot be extended to these formats. More similar.
By these formalisms, you mean coupled channels, or you
Yeah, the K-matrix.
So, okay, so in pi scattering, which is this data we discussed before, what Jose is saying is that there is a formalism, for the ones online that didn't hear it, there is a formalism called the omnes formalism, which is a dispersive formalism that is used with great accuracy and success in the elastic region. And he's asking if this can be generalized to a coupled channel like a general framework. And so the answer to that is a bit. So you can do a coupled channel omnes analysis. You can. The problem is you need to know with high accuracy all the possible final states in order to do that. If you are able to get all the data on all possible final states, then you can solve coupled channel dispersive equation for the omnes. And so you can define a coupled channel omnes equation and implement it. Problem is, as you know, yeah, that is not the case for pi scattering. Like some of the final states have been never measured. And so if you are missing one single one of them that is relatively irrelevant, then this breaks. So far, I don't know of a formalism that can accommodate missing information on a coupled channel omnes function. Also, on an elastic region, the omnes problem is analytic. So you can define the omnes function, multiply by something smooth, this all analytic. On the elastic region, this must be solved numerically. There is no algebraic solution to the couple channel roughness problem. It's just a numeric solution at the end of the day when you have the dispersive system.
And the use of Roy equation is.
Yeah, that's it's kind of related to the problem. So we are going to talk about Roy equations in the next lecture. Okay. So Roy equations are what we call full dispersive approaches to solving these scattering problems. So we'll see carry lots of problems. And again, if you want to solve them in the complex, in the couple channel region, you can, but you need to know with lots of precision, with accuracy, all the possible final states at once. And then you need to do a full dispersive approach for all the states at once. So in practice, nobody has ever done this. There are ideas. This is very cumbersome.
More questions, guys?
I think for your last slide.
Yeah,
The other one.
that one?
No. Yeah, so you mentioned, I mean, you can see on the nana there.
Yep.
The F naught 1370. Why is that not showing up in this?
Interesting. Yes, that's a good point. Very good question. So we have the non-net, and for those of you who don't know, the quantum numbers of this data is, for example, this rate is 0 plus plus, JPC 0 plus plus. This is the same JPC of these three objects here, the F naughts. That's why they are called F naughts, the three of them. So you have the same JPC. Okay. So then the question is, if this thing has the same quantum numbers as the other two, why do the other two show up in this plot that I have, but I don't have anything for the 1370 in here? And so we go back to the original reaction. So again, the reaction must be basically driven by two gluons producing pi or kk, right? Which means that we have a vertex in the reaction, this one. So we have a vertex where we are going to have gluons inside that are going to produce these states. So if our resonance doesn't couple to gluons, let's say that its gluon contact is 0, then what is going to be the value for the vertex on that resonance? It's going to be 0, right? Because it doesn't couple to this particular production process. Which means if a resonance has very little coupling to this, we won't be able to see it in data. And as you see in data, there is nothing over there. There is no 1370, neither on pi nor kk. Yeah. So the first one that you see in the first peak is what we call the 1500 here. Yeah.
So on the other hand, we have two other peaks. So what distinguishes the F naught 17?
Yes. So the idea is you can, once you get your parameterization, this one, you can tell me what is the coupling to this, right? Because you fit it to data and you got the poles in the complex plane. So now you can tell me what is the production of each one of these points in the complex plane, which one is the production of vertex of each one of these resonances. And when doing so, then you see, well, I'm comparing here 1500 and 1710, not the other two. But you see here the dominant one is the 1710. This you can also see in data. Well, yeah, I don't know if you see the numbers, but for example, comparing the 1500 and the 1710, the average is that the 1710 couples almost 10 times to kk, this is kk bar, this is pi bar. So it couples, roughly speaking, 3 point something times more to pi pi, and it couples almost 10 times more to kk bar than the 1500. So that tells you this is clearly more gluable than the other one. I don't have a plot now for the other two. But yeah, so the idea is we are calculating this production vertex, and then it's telling us which one is coupling more to that part. More questions?
At around 1.5, is there a possible other resonance at larger width, or?
I mean, this point.
Yes.
Yes. So that's another good point. So you see some great points here. So what I'm plotting in this complex plane, this is part of the complex plane. So I'm just plotting the complex plane. And if it's a smooth, I'm not plotting anything. Whenever you see a point, means one of my resamples, not gonna go into details on resampling, but one of my points in resampling the feed to the data produced a pole. So on average, everything that you see red was one pole, just with the uncertainty. Everything is basically discovering the full uncertainty. Everything you see in blue is one pole, green is another pole, the purple is another. What is this gray collection? So I didn't go through the idea that when you have parameterizations, we don't know the explicit formula, we are just inventing it based on some first principles, right? So let me go to the chemistries. Yes. So now, nothing mathematically tells me, nothing tells me, you cannot prove this, that this thing cannot generate more poles than what I am plugging in inside here. So if I put just one of these terms, naively you are going to expect one response. But it can produce many more. And this is simple to see. For example, let's go back to the last two ones. This one. Okay, this is just a function. Pi to pi. And now you are going to describe it like this. How many poles does it have? You know the answer. How many poles does this expansion have when you plug it in here? Whenever you have a complex function in the complex plane, and it's a polynomial of degree capital N, it has n zeros, right? This is basically the idea in the complex plane, is that you can always find the zeros of a polynomial of degree n, and it has n. So if I put something of order n to describe my data in the denominator, then I'm always going to have n zeros. No way around it. One of them will be my physical pole, and then the other thing will be artifacts, because I am not good enough at describing the data. So I need more parameters than QCD might predict. It's very complicated, and so I produce these artifacts. Now, this is a big problem, because if those artifacts end up very close to other poles, then they are screwing everything up. You don't really know what's going on. But if they are very far, or if they are not very relevant to your analysis, production, the couplings are very small, then it's not something terrible, right? So when doing this plot that we're discussing, this gray thing is an artifact. Okay, it's just is so far from the real axis, and the coupling is so small and appears so few times. Here I have like 200,000 poles collected for a single pole with errors, and here I have like a few hundreds. So basically, it's an artifact, and I am just going to consider it that it's not physical resonance because it's not stable. It appears only very few times, and it doesn't really matter.
Question for that.
Oh, okay, nice.
One question, guys, or? You done, maybe?
Yeah.
Sorry, this is kind of a silly question, but when
Yeah.
you were doing the parameterization for K.
Yeah.
Or well, I guess using, or not K, but the I guess in your parameterization where you have like the cotangent of
Yes.
delta. Going back to all that stuff, and you were approximating it using the polynomial.
Yes.
What energy range were you doing that over? Was it just for that low region where the function is kind of increasing there?
So this is the interesting thing. So let's go back to this. So let's say that we start by the naive way of parameterization. You get the full T, and then you put a polynomial over it, right? We have just seen that you cannot describe poles because you use a polynomial denominator, so it has no poles, and it breaks unitarity, which is not. But look at this equation. If the imaginary part is small, or the modulus is small, you are not breaking it much, right? Okay. And if the value is small, then you don't have poles. If you have poles, then you have huge value. So this might work here, and it does work here. Now, what I'm trying to stress is that doesn't matter if you put 1 or 10 parameters, it won't work here. Okay? But it will work very bad, and you will need tons of parameters. Fine. Now, for this one, because it respects unitarity, a small count on this, or basically as not so large degree of this polynomial, will be able to describe data much better. So if you, for example, use few parameters, you will describe this region. But if you use more, you will describe the whole region, because you can generate a point here by using anything else. So in principle, you can describe the full elastic region. Remember, so this is just a function, not a matrix. So you can only use it when you have an elastic region. But you can describe the full elastic region just by using expansions in the code, because you are respecting unitarity.
Although I guess this T is in, so like this T is part of another function, because I just thought like an inverse polynomial was just kind of like monotonically following all this ones.
Well, but remember that you are not expanding the full denominator, you are expanding this part.
Oh,
So
just
you
that
always have
part.
this term that is fixed. This is what gives you unitarity.
Okay.
So basically, the unitarity relation, this one, can be written in a different way. And I didn't mention it because there are too many exercises that I dropped already. But it can be said, so for example, get the inverse of this. So the inverse of t. And then calculate the imaginary part of this. This is real, right? So what is the imaginary part of the inverse of t? Minus I rho, right? So that is the unitary relation. So that is what this I rho is never expanded. If that I rho is there, then everything is unitary by construction. And so it's this thing, cancellations between this and that can produce the poles. So it's this thing, right? If you were only expanding everything in terms of a polynomial in the denominator, then you will also be breaking unitarity.
Sorry, this was just
Yeah.
kind of a follow-up question, because you said that you could add more parameters, to try to, describe, further and further on.
Yes.
Yeah, do you run into issues when you kind of consider, because, I understand like you can approximate, like one of the lower energy regions just using a handful of parameters pretty well, but obviously as you get to, higher, energies like a higher S, it
Yes.
diverges
So yes,
more and more.
sorry to
but-
interrupt you, but just before we go into that, we can describe this full energy region with this expansion with 3 parameters. 2 parameters more or less describes it. 3 is perfect. So it's not that we need 20 for that. If we do this expansion, 3 is perfect for that description. But yes, I mean, the larger the energy region, the more parameters we need.
Because I was just curious if you run into, if it like describes it pretty well over that region, or if at some like higher point, because it's a polynomial, you get like a, very big divergence from what you would expect.
No, it usually works very well. Yeah, as I said, I mean, the main requirement here is that it's unitary. So if you are respecting it by construction, it will always work well. What is problematic? I mean, many things, but one of the things that makes everything problematic when you have like a large energy region and you need many parameters is, of course, getting the errors right. And you will fit in a huge energy region with lots of parameters, and then they will be highly correlated. And these, minimas are no longer linear; they are highly correlated. And so, if you get the bare errors from a fit, you will end up with something that don't necessarily describe the honest to God errors. And so this is where resampling comes into play. You might have heard about bootstrapping data. This is what I mean by resampling.
So with these T amplitudes that are describing sort of in this case, a pi to some exotic meson back to pi. How does that correlate back to our DIS experiments where we have electron on proton, which it creates an exotic meson, which then goes to a pi system?
Well, so for example, if that was the reaction, if you have a different initial state that then decays to pi at the end of the day, and it's just a scattering. The difference, all there is an inelastic process. So you can describe it with matrices, right? So for example, let's say that you have like something like an experiment that runs on quantum problem. You have product fusion at the end of the day, the quantum numbers, it decays to something like that. It just means that you at least have a 2-to-2 matrix. Because you have that heavier channel coupling to the lighter one, the lighter can rescatter on itself, and the lighter one can also produce the heavier channel if you have enough energy, right? So at least you have a 2-to-2 matrix.
I'm also imagining though, it might have an impact on the geometric sequence that we use to get to this result, because the first term of the first interaction that occurs, will no longer look like the subsequent terms, because our initial state is not the pi, which continuously separates and recombines.
Well, yeah, but so remember that this is a hand wave introduction. You can still define this as a matrix, and this respects every principle. You can just like the same, forget about this expansion. But these are matrices already. So this accounts for all possible initial and final states. All I'm saying is whatever drives the interaction in between the initial and the final state is that particle. So let's say that you have something heavy and something light. But you can also have something light to something heavy, something light to something light, or something heavy to something heavy, to something 4 channel, 2 to 2, right? You can have it with K. All you need is different couplings in this corner and this corner. One coupling per system that you have. So if K is a matrix now, this holds perfect. Because K just has, let's look at the explicit formula, you'll see. K has a coupling. So in every vertex, you have a coupling to channel I, so this can be the heavy one, and a coupling to channel J, so this can be the light one, or vice versa. Or I to I, light to light, or J to J, heavy to heavy. So it accounts for everything. All you have to assume to do this hand wave expansion, for example, in this case, is that whatever drives the interaction between the two is a quasi-stable state. Doesn't have to be that way. When we do this, when we play with this, we usually call it, Bayer interaction, a beta salpita kernel. Some people here probably work with Dyson single equations, play with beta salpita kernels. So instead of like having a propagator, you can call it a beta salpita kernel. It's got an explanation between short distance and long distance interactions. Okay. But it holds if it's a matrix. Now the question that is also interesting, just to elaborate more, is what happens if instead of having scattering to scattering, you have production to scattering. So what happens if not everything is strobe? You have a pion and a photon gamma going to pi. That is an inelastic direction. But the vertex gamma pi isn't describing QCD. It's another kind of reaction that we consider a production vertex. So in that case, it's exactly what we're looking for here for the hybrid. Sorry that I keep switching. But this is the kind of reaction. So this would be pi gamma and then pi here. So this vertex we consider kind of a constant at the first order. And then all the scattering effects and the K matrices happening here. So that is why this as a function will have a term in the numerator that is something smooth times the denominator of the scattering. So this inverse of K minus I.
Okay, well, I would suggest that we stop here and go to a break.